All right, it is Advent of Code, day 12. I am doing it from Korea now, where the local time is 2 p.m. A little bit easier to stay awake until 2 p.m. than midnight. But yeah, here we go. About 5 seconds left. Spring with its operational damaged. What are these numbers? Groups. I see. Oh, these are the groups of damaged springs. Okay. Okay. Wow. I do not know how to do this off the top of my head. I guess I could just brute force it. How many unknowns are there? Is it enough to brute force? That's kind. We could try it. Wow, okay. Yeah, I think. Well, let me just write brute force. Let's see. Let's see. I think 2 possibilities for each. Or we could just do. What we'll do is. Damaged. Damaged is. Pound. Okay. Basically. This is equal to G. Sum of the counts. Okay. This should start at 0. Because we're not producting. Am I still printing? I am still printing this. Okay, that seems like it's going fast enough. Let me get rid of this and then rerun. It's definitely going to be slow on the longer ones. I'm going to copy in the sample input just in case. Nope, there's our answer, 7118. Rank 16. unfold. 5 copies of itself. 5 copies of itself. This is a lot harder. I don't see an easy way to abuse the fact that it's 5 things repeated. Because it's not like the first fifth needs to correspond to the first fifth. The first fifth of unknowns could all be empty, and then, well, I mean, this is pretty constrained. How long are these? Would it be faster to, like... What's annoying is that these kind of blend in with the unknowns. It's like this here could be a group of 6, or it could be like a 3 and then a 1, or it could be a 4 and then a 1, or a 3 and then a 2. It's just like very annoying to do. Yeah, multiplying by 5 actually means that this brute force is definitely not going to be fast enough now. So I guess you know the length of this. This doesn't really imply the size of the other gaps. You know there has to be at least 1 in between each of them. And you know that that's everything. So, can you do like a recursive thing? On the first position, you either like insert a group or you don't. I think you can do that. Okay. I think this is just like a recursive thing. Okay, so the question is, what are the remaining groups? So we have some string, some remaining groups. I'll write this the inefficient way first, and then I can optimize it later if I have to. These are the remaining groups, and basically, if this is a fixed case, if we're out of characters, if we're also out of groups, then 1 arrangement. Otherwise, if we still have groups left, 0 arrangements. And then what we can do is we can either try and put a group, try and put the next group, or we can insert an undamaged. So I guess first, if it's undamaged, then we just recur on this. It's interesting. I don't know what setting I just toggled. Hopefully that's fine. And the groups are unchanged. Oh, it was caps lock. I forgot to rebind that. If it's this, then this is sort of a little awkward. We need to like consume as much of the group as we can. So I think what we want is we want like a group in progress. Do we really want to do it this way? Yeah. So group in progress. This will be none. If okay, so this needs to be group in progress. None win 0. And basically what we'll do, so this will have to set group in progress to none. If this was is not none and greater than, I'll just do this. If we were trying to do a group in progress, then there's just no configurations as soon as we see this. If we see this, then we can work on the group in progress. If it's not none, this is just really annoying the way I've written it. Because if group in progress is none, then we have to match, like once we finish okay, if it's 0, so here's what I'll do. 0 means we have to match an undamaged. None means we have optionality. So we'll do that. So like we have some optionality if we've like seen an undamaged one. We could either start a damaged group or we could keep doing undamaged. But if we just finish a damaged group, then we need to have an undamaged one. Okay, so let's rework this. If we're out of characters, out of groups, and we either are 0 or none, then we would return this. Otherwise, if we're out of characters, we don't have anything. Okay, now if we're this, so if GAP is not none and greater than 0, then we wanted a match thing and we can't, so we just fail. Otherwise it was none or 0, and since we saw this, now it's going to be none going forwards. That's correct. If it's this, then if it's not none, we just decrement it and we're good. If it's not none and greater than 0. If it is not none and it is 0, then no configurations. Otherwise we just decrement the group and keep going. If it is none, we need to pop out the first group. So new groups is this, and then the group in progress is group 0 minus 1, because we're working on that. If the group was 1, that's fine, this will just be 0. And now our number of configurations is group in progress, new groups. Whoops, I should not redefine this. That would be bad. Okay, so now we started working on the group. That's great. This was the none case. We had optionality. If it's a question mark, well, if group in progress is not none and it's greater than 0, well, we need to work on this group. So that is just this case. So if it is equal to 0, then that is just this case. So now we're going to treat it like a dot, like an undamaged one, and we move on because GIP was 0, so we had to finish the group. Otherwise, GIP is none. This is the only place we have optionality, and we can choose to either make it a damaged or undamaged. So this is going to be, if we choose to make it damaged, what that's going to do is so we keep going. We need to use the next group. By the way, whenever we do this, this only works if len groups greater than 0. Otherwise, we have no possible configurations. Okay. If we have groups left, then we can make it damaged, and we can use the new GIP will be group 0, and the new groups will just be groups 1 colon group 0 minus 1, because we use the thing. If undamaged is just going to be the case like so. If it's undamaged, now we have optionality, and then groups are unchanged. And we just add these up. I think that's good. This should just be okay. And then for starters, let's see if this gives me the same answer in the previous thing. I have a feeling this will be quite slow. Okay, so the first thing is just the string. This is just A. And then GIP will be none. We have optionality. And the groups are just G. Uh-oh, what did I do? What? Oh, I did this. GP equals none. Yeah, I can't do that. Okay, I think that's fine. Same answer. That's beautiful. That is extremely beautiful. Please don't be too slow. Oh, no, I think it's too slow. Let me use J instead. I could DP this, add a cache. I could also make this faster by, instead of doing string slicing, just keep an index. What is the fifth one? Or the seventh one, actually? Okay, 1, 2, 3, 4. Oop, this is 4. 5, 6, 7. Why is this one harder? 2, 3. There's a lot of groups here. S I I just don't know how far it got. I think the cache is the better thing. Oh my god, am I forgetting the Python cache? Oh, functools.cache. I have it imported, right? Whoa, it does not like that. What's the list that it doesn't like? Is it just groups? Because groups is a tuple. Whoa! That's like scary how fast that is. Is that real? Oh, that's an answer. That's an answer. Please be right. Please be right. No, it's not right. Oof. Okay. That cache really sped it up. Like more than I would have thought. If we don't do... Oh wait, is it still asking for the sum? Yeah, it is asking for the sum still. As it should be. And just to make sure... Yeah, that's the right answer. Okay, well, this is a little sad. The above example, after unfolding, this is the example... Okay, let's do that. The answer in the old example was 21. Okay, and then there it's that. Okay, that's not the same, so that's good. I can just check this. What does it get? Oh, 0. 0 is wrong. 0 is very, very wrong. Okay. Shoot, why is it giving me 0 there? Wait, that is from that, right? Recur, if the string was... I think it was this, none, and then it's like 1, 1, 3. This says 1. But now, if we do 5x this... Oh, wait, yeah, 5x this should be 0. Sorry, did I misunderstand? Because now we can't... Oh, wait. Oh, with a question mark in between. Oh, no. Oh, that is... That is so sad. Okay, double check this. That's the right answer. No. I gotta get rid of the print. Where did my print go? I already got rid of it. Right? Okay, new answer. Rank 53. Okay. Oh, I leaderboarded both parts. 53 was not as high as it probably could have been. Let me see how much, like, that was definitely like 2 minutes of wasted time just because I did not read this. So let me see what that would have cost me. 17 minutes and 14 seconds would have been 36. Okay, it didn't cost me as much as I thought it did. Wow, 5 minutes, like 6 minutes is insane here. as like the top person. Huh. Oh, and once again, I'm right below Antonio in submitting, at least for part 2. He finished. Oh, I finished faster than him on part 1. Okay, that's cool. Whew, yeah. Well, that is Advent of Code, day 12. Hopefully I go up a little on the leaderboard for this. Did I? I think I might have been 16 before. Oh well. Anyways, yeah, good to get points after 2 days of 0 points, and yesterday of doing it on the plane. Cool, so I guess I'll say a little about the problem today. So basically, the problem says you have these strings of like dots and pound signs, and then you have another thing that describes the groups of the pound signs only. So 1316 says it's a group of 1 pound sign, 3 pound signs, and 1 pound sign, and then 6 pound signs. And this has to be separated with the dots. And then what they say is, well, actually, we have some question marks. Question marks can either be dots or pound signs. And the question is, given some configuration like this, where you have the question marks, you have the pound signs, and then you have the number of the groupings, how many possible distinct group like assignments or possible actual things are there that would give you this? So basically the unknowns can either be dots or pound signs, and you don't know. And the question is like, how many possible unique things satisfy this? This is definitely a question where when I first read it, I sort of thought like, wow, how am I even going to approach this? And the first thing I sort of did was I looked at how many question marks do we have per line. So this is the example input, and this looks fine. But of course, like the real input can often have significantly more. And I looked at it, or I think I even printed out like at the top. This is actually a little annoying too. I'm using like a newer version of Python and idle, and this one didn't seem to respond as well to my Control-C keyboard interrupts. But anyways, I printed out the number of question marks per line, and I got things like this. And this basically tells me that brute force. So what is the brute force solution? The brute force solution is try every possible assignment of dots and pound signs to the question marks, and then just run through and check to see if it satisfies this. So if you have like a length k string, and you have like m question marks, the efficiency of this is like O of 2 to the m, because you need to try every possible configuration. So each question mark can either be a dot or a pound sign, so that's 2 per, and they multiply. And then once you have a configuration, you need to actually run through it and check to see if it matches this. That you can do in linear time by just going through and tracking the groups. So it's O of 2 to the m times k. And here I saw that m is like on the order of, I think the largest one was like 20 or so. And 2 to the 20 is like kind of slow. But anything less than that is like quite efficient. Even 2 to 20 is quite doable. I think if I saw things that were like, well, to be clear, I think these problems will generally either be completely unfeasible to do like exponentially, or they will be completely reasonable to do exponentially. Mostly because if there was something in between, then like there'd be some hardware language advantage that I assume is undesirable for these problems. I'm just talking about like when Eric designs them. But in any case, if I saw like 30s, 2 to the 30 is like probably unfeasible. If I had to do it once, then maybe. But if you have to do it for every line, then that's definitely not going to work. Whereas like 20 is fine. I think 24 or something is like my mental idea of where the limit is. This is like 16 million things. It definitely depends on like your constant factors when you're around that range. Or 2 to 24 for like if you have a lot of different lines. And again, also in Python, you could probably push it higher if you're using a well-optimized language. Well, anyways, I saw that and I'm like, okay, we can brute force this. So I wrote the brute force. The brute force is, I implemented it with itertools.product. So you can figure out so qpos is the positions of the question marks in each string. And what I do is I just like, for every possible thing here, so here I can even demonstrate what this looks like. I'll just set QPOS to like 3, 5, 6. And you can see we just get like every possible configuration. And once I have a configuration, I just go through and I assign it into Q. And I have Q set as a list, so I can assign it. And then I just do the grouping. I wrote this group function, which actually just like does the thing of iterate through and then sort of try and group. L is the size of this current running group. And if the grouping matches, then it just adds 1 to a counter. And then when we're done, we just add this to the answer. And this works fine for part 1. Part 2 now says, okay, each line is actually 5 times the length. And the like groupings are also 5 times the length. So just like repeat this 5 times and repeat this 5 times. One thing I did not catch my first pass, unfortunately, is that it's not just repeat this 5 times, it's repeat this 5 times and then separate it by question marks. This is quite important because of course it will change the answer. But anyways, and now you can see that the question marks have sort of, like if we had on the order of, I'm trying to actually see, were there any 20s in here? I thought there were some 20s. I guess these are all like quite reasonable. Like the highest one here is maybe 14 or something. But in any case, 5 times 14 is 70, and that is way too high. 2 to the 70 you're just not going to be able to brute force. So you have to do something smarter. And the first thing I thought of was, well, I guess I thought for a little while. What I eventually decided on, but I was still unsure if it would be fast enough, is this sort of recursive thing where you like have your groupings and you can kind of go from the beginning and you can look at a question mark and go, oh, I could either put a dot here or a pound sign here. If I put a pound sign, that will just consume the first group, and then the next question mark will have to be a dot. And then you sort of just keep going. And I think in the worst case, this should sorry. In the worst case, this should be like equal to 2 to the n or 2 to the n over 2 or something. Like you can just imagine if your input was all question marks and your groupings were like half as many ones, then this just becomes n choose n over 2 or something, which is not a desirable thing to like. That would just be like very slow. But sort of the idea is that looking at these are like very constrained. When you see a 1, that adds a lot of structure to your output, because when you put a 1 here, that like forces the next one to be a dot, and then I guess it doesn't force this next one after, but you sort of get the idea. And like in actual fact, this approach, I think it should be the case that it's basically O of the number of arrangements. So if you only have 1 arrangement, this should be, it's actually not quite true. I think it's worse than that. It could maybe be made close to this. I'm not thinking too rigorously right now. I don't want to get too distracted from explaining what I actually did. The reason it's not exactly that is because it might take, like, in this case, there is only 1 configuration, and that's like assign the 1 and then empty and then a 1 to these, and then sort of keep going. But it's the case that if you choose to not assign the 1s here, you might not realize until later on in the string. You have to like backtrack up pretty far. Maybe that backtracking is like pretty bounded. I'm not really sure, but in any case, this is like a little more efficient than the actual just brute forcing thing, because it takes advantage of the structure in this. And the way I wrote that was this nasty recursive function. I ended up slapping a cache on it, so this is a memoized function. This was quite necessary to get it to actually run efficiently. I will note that this is still not like a very efficient implementation of this. I was really just spitting out logic and trying to like get the core logic in, and then thinking I could optimize it later if I had to. But I'm not going to go through this line by line. The core idea is that I've got 3 bits of state I'm tracking. I've got the string that I have left to process. I've got the groups that I have yet to think about. And then I have this GIP, which is group in progress. And sort of the idea is that if you start a group of 3, then you need to like make the next 3 things equal to damaged. They might already be damaged, in which case you're fine. Or they might be question marks, in which case you need to actually like constrain them. Or they might have some dots in them, and then it turns out that this is just impossible. And you end up in one of these impossible arrangements if you make like a suboptimal choice earlier on. So that's what GIP is meant to track. GIP equals none means that we're not working on any current thing. And I had to distinguish this from GIP equals 0, which means that we have 0 damaged things left. Because when you have optionality, when I say optionality, I mean that like we have just like put a dot down. So maybe we're like this, and we're looking at this question mark. And the groups were, so we already handled the 3 group. And then what's left is there's like a 1 group and then, I don't know, some other stuff. The idea is that like, if we were on here, then like we can't actually make this into a pound sign to consume this 1 group because that would ruin the 3 group. So we have GIP set equal to 0 to indicate that this needs to be a dot. And then the very next one, now GIP resets back to none, which means we have the optionality. We have the choice of whether to make this a dot or a pound sign. But yeah, I think that's like the core insight into what I wrote. Other than that, it's a lot of nasty logic, which is just thinking about all the casework. And yeah, you could sort of see that there's only one time where we like split one recursive call into 2 recursive calls, which is like here, and that's on the question mark, and we have the optionality. Compared to the brute force approach, where we sort of, I think that's basically similar or equivalent to like removing these checks and always splitting, because you're considering all possibilities. But here we're taking advantage, again, I'm just repeating myself, we're taking advantage of the structure in the problem and the fact that those ones let us set GIP equal to 0 and force ourselves to put like a dot for the question mark. But yeah, I think that's what there is. That's mostly all there is to today's problem. This was a tricky problem for sure. Leaderboard should be full by now. Let's take a look. I can see my final position, 17. Yeah, cool. And it took like almost 23 minutes for a leaderboard to cap today. So definitely a bit trickier problem. And I think, yeah. I guess I'm happy this worked. I can't think of any more efficient approach to this. This feels like a problem that is fundamentally pretty like this isn't, by the way, this isn't true brute force, especially because I have a cache on it. I guess I should say what this does. If you're unfamiliar, functools.cache basically adds a wrapper to your Python function, which maintains a large dictionary, and if it sees the function called again with the same arguments, it just returns what the function returned last time, and it doesn't actually recall the function. So this sort of lets you do discount store dynamic programming, where you just write the recursive function and slap a caching layer on it, and it is basically as efficient as dynamic programming. But yeah, this is a pretty handy tool when you write a recursive function, and it is slow because it's like repeating work. The way this repeats work, by the way, is that like you can imagine if you had something like this, and then your thing was like 1, 3, and then maybe there's some more stuff to do like over here, and there was some more stuff to do here. But basically, you're going to end up in the, if you put like the pound sign here versus if you put the pound sign here, you're going to end up in the same state. Oh yeah, because of that caching layer, by the way. Okay, I realized something that is kind of important I should say now. So I said at one point this is like O of the number of arrangements. If it was O of the number of arrangements, that would actually be like way too slow. And like if this is my final answer, like I just could not do O of this. That would be way too slow. And the caching layer solves that for us because there's like repeated subproblems here. So whether we put like the damaged one here, the damaged one here, either way, the number of possibilities for everything onwards will be unchanged. So we can sort of observe that like the answer to this is the answer to like this one, and the answer plus the answer to this one, and both these are the same, and they're both equal to the answer to like this subproblem where we like where we remove the one and we're just looking at this. But anyways, yeah. Cool. I just thought that was important to say as I sort of realized it. Yeah, that is all I have for Advent of Code, day 12.